Hello everyone, and welcome back to my channel, where today we're going over my newest decision tree on gas laws. As always, you can find these trees and the full solutions to the problems that I'll be discussing in this video on my website, linked in the description. Let's get into it. So just to briefly walk you through how this works, there's really only one key question when it comes to gas laws, which is a property, so volume, pressure, temperature, or number of moles of a gas, changing from the start of the problem to the end of the problem? That's it. So if we have container expanding or contracting, a gas being removed by a reaction, there's heating involved, or anything else like that, the answer to this question is yes. The only caveat is that the change must come from an existing gas. And as we'll see later, introducing a new gas into the chamber does not count as a change because there was no gas to be changed at the start of the problem. If the answer to that question is yes, all we have to do is look through the problem and identify the variables that are being mentioned, and then apply the correct equation from this list here to find whatever unknown we're being asked about. If we answer no, it's even easier. We only have to apply the ideal gas law and solve for whichever variable we currently don't have. So let's put this tool to work on some problems from the Cornell University General Chemistry course, widely considered one of the hardest in the country. Here's the first problem. Feel free to pause it and read it through. The best way to answer that fundamental gas question is to sketch the problem. So let's do just that. At the start, we have two containers, A and B, connected by a valve that is currently closed, preventing the gases from mixing. I'm also going to write in the properties of each gas in the corresponding circle. Then we have a change. The valve is opened and the gases mix, giving us the after picture there on the right. So has something changed? Well, both gases went from being confined in their individual chambers to being allowed to expand throughout the entire system. So I would say that the volume that both gases occupy has changed. That brings us down here on the flowchart, where we now just have to decide which formula to use. Here we'll look back at the question. We know we're gonna need volume, because that was what changed. And we also see here that both gases have a pressure associated with them. So we'll use this formula, P1V1 equals P2V2, that incorporates both volume and pressure. Let's take a look at the equation for each gas individually and figure out what we already know and what we still have to calculate. For gas A, we're given the initial volume and pressure, and though it might not initially be obvious, we actually do have that final volume, V2. Since chamber A was 800 milliliters and chamber B was 120 milliliters, after the gases mix, they'll each have 920 milliliters of room. So that's our V2. We're clearly solving for P2 here, that's our only unknown. So after rearranging and substituting, we get that the final pressure of gas A is 2.61 atmospheres. Now, the very crucial detail here is that this is the pressure of gas A only, not gas B. In other words, this is the final partial pressure of gas A. Doing all of the same steps for gas B, we find that its partial pressure is 0.65 atmospheres. Now, what do we do with this information? Let's take a second look at what the question was asking for, which is the partial pressures of both gases and the total final pressure in the combined chamber. We already have the partial pressures, and to get the total pressure, we can just take a look down here at the useful equations section of the chart, where we see that the total pressure in a chamber is equal to the sum of all of the partial pressures in the chamber. So we'll just add up our two partial pressures for gases A and B for a calculated final total pressure of 3.26 atmospheres. Let's look at another example. Again, feel free to pause, read the question. And again, we're gonna start with a quick sketch. We'll start with a container with a volume 5 liters that has 180 grams of bulandiol, either solid or liquid, which has not yet been vaporized, as well as 1 mole of neon gas. Then, after the vaporization step, the container contains that same 1 mole of neon, plus an additional 180 grams of bulandiol in the gaseous state. And the key fact that's going to help us here is that only gases can exert pressure on a container, not solids or liquids. So again, the key question, is a property of a gas changing from the start to the end of the problem? Well, something is definitely changing here. The bulandiol gets vaporized or turned into a gas and will begin to exert pressure on the walls of the container. However, this does not qualify as a change under our definition because bulandiol was not a gas to begin with. So there are no initial properties to change to final properties. Since we answered no to the question, we're going to be using the ideal gas law. Pressure times volume equals moles times the ideal gas constant times temperature. We're going to have to apply the formula to each gas separately with the goal of filling in any remaining information that's not already known to help us solve the problem. Considering neon first, we see that we have 1 mole of it at 310 degrees Celsius in a volume of 5 liters. So we can check off V, N, T, and R because R is a constant, so we've always got that. And now all we have to do is solve for the pressure that neon is exerting on the container. Substituting and rearranging, we find that neon exerts 9.57 atmospheres of pressure on the container. For bulandiol, the volume of the container and the temperature are the same as for neon, but they give the amount of the compound in grams, not moles. so we don't actually know N yet. Can we figure out pressure? Well, we know the total pressure, and we just found the partial pressure of neon. We also learned in the last problem that the total gas pressure in a chamber is just the sum of the partial pressures, which in this case is just neon and Bohlen-Dial. This lets us solve for Bohlen-Dial's partial pressure. Plugging this back into the ideal gas law, we can rearrange and solve for N, which comes out to 0.65 moles. Now that we have all the information, what can we do with it? Well, two things I always ask myself at this point are A, what is the question asking for? And B, what information have we not used yet? They want the molecular formula for Bohlen-Dial, and for that we'll always need the molar mass and the empirical formula, which we already have. To get the molar mass, which has units of grams over moles, we need the mass in grams and the moles. And it just so happens that the only information we haven't used yet is the 180 gram mass of this sample of Bohlen-Dial. So dividing mass by moles, we get a molar mass of 279.6 grams per mole. Finally, to get molecular from empirical formula, we have to ask ourselves how many empirical units go into the molecular weight. The mass of the empirical formula is 138 grams per mole, and if we divide the molar mass by that, we'll get a ratio of 2, which tells us that we have to multiply the empirical formula by 2 in order to get a final molecular formula of C18H28O2. Okay, that's all for this video. If you want more free information, check my website and YouTube, link down below. And if you like the way I teach, I offer private one-on-one tutoring, which you can also find in the description. Let me know what I should cover next.